This is Rich Taylor, Miami University. The topic of this presentation is modular glassware and the setting up of a reaction apparatus in the organic chemistry laboratory. The objectives are to understand the notation that's used for standard taper glassware, the use of stopcock grease to facilitate this assembly and disassembly, and how to most efficiently assemble the apparatus needed to carry out an organic reaction. The reason why we need to have these kinds of kits and setups for modular glassware is that the different kinds of reactions that organic chemists run are really quite varied. They require a wide variety of setups in order to be carried out efficiently, and to invent a new piece of glassware for every kind of reaction is not practical, and so we take the apparatus, break it into component parts, and assemble them in various ways to get the material we need. The best way to do that is through standard taper joints. As you will see in various laboratory setups, these are ground glass fittings so that they fit together very nicely. They'll allow a good seal to fit as the pieces come together so that there are no leaks and the entire apparatus is as close to one piece as possible. The notation for standard taper joints shows the dimensions of the inner, outer, and outer joint pieces so that they'll combine to form a good seal. In the typical sophomore organic laboratory kit, a 1922 joint is the most common. Those two numbers refer to the dimensions of the joint. The 19 refers to the diameter of the joint at its widest piece. So you can see here that this mock-up of an outer joint, the 19 refers to the diameter at the wide end. 22 is the length of the joint. And so you can see this one extends 22 millimeters down the tube. It goes from a wide opening of 19 to a narrower opening at the bottom through a standard taper. That standard taper is for every 10 millimeters of travel, the joint gets narrower by 1 millimeter. That's the standard taper. And so all 1922 inner joints and 1922 outer joints will fit together and create a nice single piece. It's important when using ground glass joints to use stopcock grease. Stopcock grease ensures a good airtight seal at the joint, and it also assumes that the joint won't freeze, that once you put it together, you'll be able to take it apart as well. Stopcock grease is a silicone sealant lubricant that's perfect for the job at hand and tolerant of the kind of temperatures you use in organic reactions. It's important to use the right amount of stopcock grease. The best process for applying stopcock grease to a joint, and you'll need to practice to get this to work best, is to apply a narrow band of stopcock grease on the inner joint all the way through the length of the joint. At that point then you can combine the upper and lower joint and turn the entire joint assembly 360 degrees. This should create a thin film of silicone grease through the entire dimensions of the ground glass union between the two. If you use too little stopcock grease, you'll run out of grease before you make the entire circuit. If you use too much, you'll see stopcock grease oozing out of the top and bottom of the juncture of the two joints, and with a little bit of practice, you'll get a good knack of applying just the right amount. Once a reaction's finished, you should immediately disassemble the entire apparatus and clean the ground glass unions before you return them to the laboratory drawer. As a result then, what you should think of is that every new setup should be made with new stopcock grease, and it should be thoroughly cleaned before it's returned to the lab drawer. On the next couple slides, what we'll show is just a few common setups for doing reactions. In this one, we have a very common way of running reactions, which is heating to reflux. In many organic reactions, it's important to control the temperature. The best way to control temperature without elaborate electronics is to recognize that if a solvent's boiling, it's at a certain temperature, whether it's boiling vigorously or rather leisurely, the temperature will be the same. And so you can control the temperature by just making sure the solvent's boiling. If you run the solvent at the boiling point, though, you don't want to lose any of the solvent. You don't want all the solvent to boil away before the reaction's done. And so this is a common system to heat at what we call reflux, or at the boiling point. And so you can see that the round bottom flask with the liquid is close to the heat source, and a condenser is placed on top through a ground glass joint. That condenser is a water jacketed tube. Water goes in at the bottom, out at the top, so that the water completely fills the jacketing around that tube. And so now as the liquid refluxes or boils, the vapors go up, they're cooled by the cooling jacket and return to the flask. So we can heat at that boiling point temperature as long as we want without losing all of the solvent. A more elaborate setup is the one for distillation, where you can now see that your heated liquid now is going to have the vapors not returned to the original flask but transferred to a new one. And so you can see then that instead of a vertical condenser, we use ground glass joints to have a new union, one where we can put a thermometer at the very top, but now we have a takeoff that allows the vapors not to be returned to the original flask, but now to go down a condenser and condense onto a new flask. A couple points to note here is, once again, the water comes in at the bottom, out at the top. There's a place here for a thermometer, but it's important, as you have the entire system set up, that you not heat a closed system. There always has to be an opening in order to allow pressure to equalize, so that we're not going to have a hazardous explosive type of situation. And so you can see here that this hose barb is the place where we have the pressure equalization. In the previous slide, we left the condenser open to the air at the top. You should never stopper this or never close off the hose barb, because you don't want to be heating a closed system. Well, the last two slides showed the condenser and the flask set up sort of in midair. Obviously, we have to support these things. We'll use ring stand and clamp for that. The important thing to keep in mind is that you cannot count on stopcock grease to overcome gravity. If you set up a reaction so that a flask is sitting in midair and it's only being held by stopcock grease attachment to another piece of glassware, you're bound to be disappointed and wind up with broken glassware, usually at the most inconvenient moment. The connections then need to be clamped properly. If you underclamp, you've created a system where things can fall apart. If you use too many clamps, however, sometimes the tightening of the clamp will actually break some of the ground glass seals, and you'll actually create links. So what you want is as few clamps as possible, but enough to completely support the structure. And you should plan out your reaction setup in such a way as to facilitate that. Oftentimes, students, particularly beginners, will take an awful lot of time trying to set up a reaction just right, and normally it's because they've not constructed things in the most efficient fashion. The best way to set up and attach things to a ring stand is to start by clamping the clamp to the glassware first, and then clamping the flask and clamp to the ring stand at exactly the right height. You should start at the bottom and insert your flask into the ring and then onto the ring stand at just the right height, and then build the apparatus from the bottom up, clamping wherever necessary. In this way, you don't have to attach the clamp to the ring stand, then attach the flask, and then readjust it and sort of go back and forth. This will make as few constructions as possible to get there. With this in hand, and as you begin to gain knowledge in putting together reaction flask, you should find that the overall process is going to become second nature to you.